In this video, I want to talk about the node voltage method. So if you remember from a previous video, I discussed that using the systematic approach, we can significantly reduce the number of simultaneous linear equations that we need to solve. But even then, for a relatively small circuit, we ended up with more than necessary equations. So even though the systematic approach is very good, we said that we need to make some changes to the variables that we define. So if you remember, for any component in the circuit, we use either their voltage or their current for solving that circuit. But we said that what if we change those variables instead of going for voltage and currents of individual elements, we go for voltages at essential nodes, or we go for currents in meshes. So in this video I will talk about how we can use the node voltage method instead of using the regular technique that we did before. Of course, keep in mind that we are still using Ohm's law, KVL and KCL. Nothing has changed with that regard, but we take these techniques to a different level with the definition of the voltages at nodes or the currents in meshes. So let's just take a look at this very basic example. So we have this independent voltage source. The value is 10 volts. We have the positive and negative polarities like this. It is connected to a 1 ohm, a 2 ohm, a 5 ohm, and a 10 ohm resistor in this configuration. And finally, we have this independent current source with the value 2 amps that is connected here. So how many nodes do we have in this circuit? So if you remember, a node was a point where two elements are connected, at least two elements. So this, you can say, is a node, because that's the point of connection of this 1 ohm and this 10 volt. Then this is another node. 1, 2, and 5 ohm resistors are connected at this point. Then we have this node where we have the 2 ohm, the 10 ohm, and the 2 amps getting connected. And finally we have this node at the bottom where the 10 volt, the 5 ohm, the 10 ohm, and then the 2 amp are connected. So out of these 4 nodes that we have for this circuit, how many are essential nodes? Because that is important. So what was the definition of an essential node? An essential node was a node at which 3 or more elements were connected to it. So out of these 4 nodes, this one is not an essential node because it's the point of connection of only 2 elements. But this, and this are all essential nodes. So we have 3 essential nodes in this circuit. So since we have 3 essential nodes in the circuit, we can define NE minus 2, so NE equals 3. So we can define NE minus 2 or 2 node voltage equations to describe this circuit. So how should we do that? So the first thing that we do is that we consider one of the essential nodes as the reference node. So it doesn't matter which one of these 3 you choose. So either this node, which I named it 1, this one which I named it 2, or this one which I name it 3. So either of them is fine to be used as the reference node. So what happens is that we measure the voltage of each of these nodes with respect to their reference node. So that is an important point. So practically speaking, the essential node is usually chosen as the node with more branches, because that helps us simplify our equations even further. So between 1, 2, and 3, 1 has 3 connected components, 2 also has 3 connected components, but node 3 has 4 connected components: the 10 volt, the 5 ohm, the 10 ohm, and then the 2 amps. So because of that, we considered node 3 as the reference, and we use this symbol to show the reference. So this is one of the symbols that you can choose. Another symbol is usually like this. So you can think of this as the ground for your circuit. Why do I say ground? Because whenever we want to measure voltage for the node, we measure the voltage of the node with respect to the reference. So considering it as a ground is a good conceptual decision that we can make. We basically say this is the ground, so ground has a voltage of 0, so that's why we call it the reference or the ground. So that's the first thing that we need to do. Find the nodes, find the essential nodes, find which one of the essential nodes have the largest number of branches, and we consider that as the reference node. So as I said, the node voltage is defined as the voltage rise from the reference node to a non-reference node. So since we are measuring the voltage with respect to the reference, right, and we conceptually assume that the reference node has a voltage of 0, so for assigning the polarities for these nodes, we consider the ground or the reference node to have a negative polarity, and the other nodes to have the positive polarity. So that's why we call this node voltage as the voltage rise from the reference node to the non-reference node. So we have node 1 with the voltage V1 from node 1 to the reference, and we have V2 for the voltage for the node 2 to the reference. So as you can see here, now we only have 2 unknowns to solve. So one thing that you can notice is that V1 is the voltage across this 5 ohm. Also V2 is the voltage across this 10 ohm and then this 2 amp current source. But what about the rest of the elements that we have? What is the voltage across this 2 ohm? Using the systematic approach, we assign individual voltages or currents to the elements, right? But when we are using node voltage method, we don't do that. Instead, we use the voltages at the essential nodes, basically. So if we want to find the voltage across these 2 ohm, what we can do is that we can assign a polarity, something like this. Let's just call this V2 ohm. And V2 ohm equals, given the polarity, it is V1 minus V2. So after we found out the value for V1 and V2, getting the voltage across this 2 ohm is easy. We just do this simple calculation. What about across this 10 ohm? Sorry, this 1 ohm. So the voltage across this 1 ohm, again, assuming that we have this polarity, it is going to be V1 minus this 10 volt, right? So since these calculations are not that hard and practically do not require solution of any linear system equation, that's why the node voltage method is preferred in comparison to the systematic approach. Why? Because we reduce the number of simultaneous linear equations that we need to solve. So now, what is next? The next step in the node voltage method is to write KCL equations for the non-reference nodes. So we have this non-reference node, we have this non-reference node. So we need to write the KCL equations for these individual nodes. But for the KCL equations, if you remember from before, we usually said that, okay, we consider individual currents for the elements that are connected to the node. And then we use that to say, let's say KCL for node 1. We use that to say, okay, we have I1 entering the node. So let's consider it with the negative sign. We have I2 leaving the node. Let's consider it with the positive sign. And finally we have, let's say, I3 exiting the node 2. I consider it with the positive sign too, and then we have 0. Right? So this is what we used to do when we wanted to write the KCL for these individual nodes. But the whole point of the node voltage method is that we get free of defining these individual currents for the elements. Instead, we want to use only the node voltage variables. So we only want to use V1 and V2 to write our equations. So to do that, what we can do is that, considering the passive sign convention, for each node we write the current for the branches that are connected to the node as leaving currents. So basically we consider that for node 1, for example, we have a current that leaves node 1 and goes through this 1 ohm. For this 5 ohm, we consider having a current that leaves a node 1 and enters this 5 ohm. And finally, for this 2 ohm, we consider a current that leaves node 1 and enters this 2 ohm. So how can we write these equations based on V1 and V2? The answer to that is very simple. If we consider a current leaving node 1 and going through this 1 ohm, following the passive sign convention, we have a positive polarity here and a negative polarity here. So that means that the current that goes in this direction through this 1 ohm resistor is basically the voltage across this 1 ohm divided by its value. So what is the voltage across this? Since the positive side would be here, the negative side would be here based on the passive sign convention, the voltage would be the voltage at node 1 or V1 minus the 10 volt divided by 1 ohm. So I have this portion of the circuit magnified here. So we have this node 1. We want to consider a current, I call it with the generic name I, that leaves node 1 and goes through this 1 ohm resistor. Following the passive sign conventions, we have the positive side and the negative side here for the resistor. The voltage across this resistor is going to be I, the current, whatever that current is, multiplied by R. But what is that current? The current is the voltage across this resistor divided by its value. So we have V1, the voltage at node 1, minus 10 volt, the voltage at this node, which is not an essential node, divided by 1 ohm. So this is the current that goes through the 1 ohm resistor. And based on the relationship that we put, actually the current goes from the right side to the left side. So this is for this one. What about for the current that leaves node 1 and goes through this 5 ohm? If we assume a current in this direction, which makes the polarities to be like this. The current that leaves node 1 and goes through this 5 ohm is the voltage across this 5 ohm divided by the value of the resistor, which is 5 ohm. So what is the voltage across this 5 ohm? The voltage is going to be V1 divided by 5 ohms. So we basically don't have this subtraction anymore. Why? Because the voltage across this 5 ohm or the voltage at node 1 is already calculated with reference to this node underneath the circuit, right? So since that's the case, we only have the voltage at node 1 by itself. Or you can think of it as V1 minus 0 divided by 5. Both of them result in the same thing. So the current that goes here is V1 minus 10 over 1 ohm. The current that goes through this resistor is V1 minus 5. What about the current that leaves node 1 and goes through this 2 ohm? Again, for this element, following the passive sign convention, the positive sign and negative sign for the voltage polarity will be in this configuration. So what is the current? It is going to be V1 minus V2 over 2 ohm. So this is going to be V1 minus V2 over 2 ohms. So now, as you can see, we have all the currents that leave node 1 written in terms of V1 and V2. So without any addition of new variables like currents of these individual resistors, we were able to write the KCL for this node based on the two variables that we use, the node voltage variables. So if I want to summarize this, I just say KCL at node 1. It's going to be V1 minus 10 divided by 1 plus V1 divided by 5 plus V1 minus V2 divided by 2 equals 0. So that will be the first equation that we needed. Since we only had to find two node voltages, we only need two linear equations. So that is one of them. How do we get the second one? The equation for this? We do the same thing. So we write the KCL at node 2. Again, we consider all the currents are leaving node 2 because we want everything to be consistent, right? So based on that, we write down the equations for KCL for this node as well. So if we have a current leaving node 2 going through this 2 ohm, the polarity following the passive sign convention would be like this. So what is the current here? It's going to be V2 minus V1 over 2 ohms. Plus, what about the current that goes through this 10 ohm? So since the voltage across this 10 ohm is actually V2, we have V2 by itself divided by 10 ohm. And then finally, for this, we have a current that leaves this node and goes through this 2 amps independent current source. So what is that current? So since we have an independent current source, that is basically the current. So since we consider the current to be leaving, but in reality the current is actually entering the node, we use it with a negative sign. So -2 equals 0. So that is the second equation that we need to have. So these are the two equations that we need to have. Let's just go over them one more time. We find all the essential nodes. We consider the essential node with the most number of branches as the reference. And we define our node voltage variables at the voltage rise from the reference node to each one of those individual remaining essential nodes. So we have V1 and then we have V2. Then for these two essential nodes, node 1 and node 2, we write the KCL in terms of the currents leaving these nodes and considering the voltages at the nodes as the variables. So we have a current leaving this node going through this 1 ohm. What is the current? Basically the voltage across this resistor, which is V1 minus 10 volt divided by the resistor. So we have V1 minus 10 divided by 1. The same for this one. For this one, since it is the voltage across this 5 ohm is actually V1, so we write it as V1 minus V1 divided by 5. So that is the basic Ohm's law. For this one, we write it as V1 minus V2 divided by 2 ohm, and that equals 0. Then we do the same for the second node. Again, we assume all the currents leaving because we want everything to be consistent, right? When we considered all the currents to be leaving node 1, we came up with a plan to do it very straightforward. We do the same for this node too. So we have V2 minus V1 divided by 2 ohm. That is this current. Then we have V2 divided by 10. That is this current. And finally, we have the -2 amps, which is this current, right? Since we assume that the direction of the current is leaving node 2, but in reality it is entering node 2, that is the reason for having this negative sign. So now we have these two equations. So what is left for us is to basically solve it. So I can rewrite these equations in a much nicer form. So what I can do is that I can write it as 1 plus 1/5 plus 1 over 2 V1 minus 1 over 2 V2 equals 10. So that is this equation. For the second one, we have -1 over 2 V1 plus 1 over 2 plus 1 over 10 V2 equals 2. So this is basically a 2 by 2 linear system that you already know how to solve. So if you solve those two equations, these are the results that you get. So V1 would be 9.09 volts and V2 would be 10.91 volts. So can I ask you this question? Can we say that the circuit is solved now that we have V1 and V2? You probably think that the answer to this question is no. But in reality, it is yes. Why? Because as I said before, there is nothing left in this circuit that we cannot find by basic algebra using V1 and V2. So let's say if we want to find the voltage across the 2 ohm resistor. So let's just say I say the voltage is in this polarity. So this is the V2 ohm. If it's in this polarity, that means that it is V1 minus V2. So it is V1 minus V2, which equals 9.09 minus 10.91. So what is this value? It's going to be negative. So 10.91 minus 9.09. So it's going to be 2, 8, and then 1. Negative 1.82 volts. So the voltage across these 2 ohm, considering this polarity, is going to be negative 1.82. What if we said, okay, the polarity was different, was in this direction? Let's just call it V2 ohm prime. So V2 ohm prime now equals V2 minus V1, which is 10.91 minus 9.91, or 1.82. So as you can see, depending on the polarity that we can define, following the passive sign convention, we practically get the same result, right? Having V2 ohm in this polarity equals having V2 ohm prime in a reverse polarity, right? When we chose the polarities wrong, you might say, we ended up having a negative value for the voltage. So nothing has changed. What about other things? What if we want to find the current that goes through this 10 ohm? So the current of the 10 ohm, I call it I10 ohm. So the I10 ohm equals V2 divided by 10, or 10.91 divided by 10, which is 1.091 amps. So as you can see, it is very easy for us to find the individual variables for the elements. So that's why choosing the circuit variable as the voltage and currents of individual elements is not 100% I would say beneficial, because there are some calculations that you can easily do by basic algebra. You don't need to solve simultaneous linear equations for that. So the node voltage method and the mesh current method are ways for us to basically get the bare minimum number of equations that we need to solve in order to be able to say we have solved the whole circuit. So we get to a point where everything else can be done with simple algebra without the need to solve simultaneous linear equations. So now that we have this, let's just take a look at a little bit more complex circuit. Let's just see if we can get it to the same point as before. Basically, get from the circuit to a set of linear equations. So as you can see here, we have a 20-volt independent voltage source. We have two 2-ohm resistors, one 5-ohm, one 20-ohm, and one 10-ohm. And here we have this additional current controlled voltage source too, that a little bit complicate the processes. So let's just go through the steps one by one. First, what are the nodes that we have for this circuit? So we have this as the node, this another node, this is another node, this is another node, and finally this one is the last node. So how many nodes do we have? We have 5. So out of these 5, how many are essential nodes? So this node here and this node here are not essential nodes. Why? Because they are the point of contact of only 2 elements. So the essential nodes were the point of contact of 3 or more elements. So considering that, we have this node, and this one as the essential node. So now we need to consider one of the nodes as the reference. So which one should we choose? Generally, we go for the node with the highest number of connections. So out of these 3 nodes, this one has the highest number of connections because 1, 2, 3, 4 elements are connected to this node. While for this one and this one, there are only 3 elements connected to it. So we consider this as the reference node. And then I assign the numbers for the individual nodes. I say this is V1, and this one, I say it is V2. So now that we have this, we need to write down the KCL based on the currents leaving these nodes and going through the connected elements. But we don't define any individual current variable. We use the node voltages to write those currents. Okay, so let's just go do this for node 1. We want to find the current that leaves node 1 goes through this 2 ohm. So we have V1. So this is for node 1. We have V1 minus 20 volts divided by 2 ohms, plus we have this one, which is V1 divided by 20. So we have V1 divided by 20. And finally we have V1 minus V2 divided by 5. So V1 minus V2 divided by 5, and that equals 0. Let's just do the same for the second node too. So for the second node, I want to write the current for this branch first. So it will be V2 minus V1 over 5. So V2 minus V1 over 5 plus V2 over 10. V2 over 10. And finally, for this one, we want to write the current that goes through this 2 ohm based on the circuit variables that we have, V1 and V2. But the thing is that what we have here is a current controlled voltage source. So we treat it the same way as we did here, right? But instead of using the exact value here, we have an equation. But it still works the same. So I write it as V2 minus 8 I phi over 2 ohms equals 0. So this is the first equation. This one is the second equation. But if you look at these 3 equations, you see that we have only 2 equations, but we have 3 unknowns here. We don't know V1, we don't know V2, and also we have this I phi that we don't know either. But can we find I phi based on V1 and V2? The answer to that is yes. This is I phi, right? Remember when we wanted to come up with the current that goes through this 5 ohm and it's leaving node 1? We said that we calculated by writing it as V1 minus V2 over 5 ohm, right? So as you can see, this current is exactly the same as I phi. So what we basically do is that we just say I phi equals V1 minus V2 over 5. So this you can say is an additional equation that we use basically to supplement the equations that we had. So based on this, what we can do is that we can update equation 2. So we have now V2 minus V1 over 5 plus V2 over 10 plus V2 minus 8 V1 minus V2 over 5 over 2 equals 0. So that is the updated second equation that we have. So now using equations 1 and equations 2, we can find the values for V1 and V2. So I highly suggest you do the calculation yourself. You can refer to the textbook too to find out the final values for V1 and V2. But for all intentions and purposes, when you find the values for V1 and V2, we practically know everything that we needed to know about this circuit. Any other variable or value can be easily derived using V1 and V2. So that's why we use node voltage method to basically help us get rid of all those unnecessary equations. So in this video, you got introduced to the node voltage method and you saw that how it can be beneficial in reducing the number of equations that you need to solve simultaneously to get the solution of an electric circuit.